Hi everybody. In this video I'm going to describe the physical quantity known as torque. First I'll provide a fuzzy conceptual description and then I'll provide a more detailed mathematical description. Alright, here we go, starting with a fuzzy conceptual description. Imagine we have a really sticky nut. It resists turning this way and it resists turning this way. It's really hard to start turning. So what do we want to do? We put a wrench on it. How do we use the wrench? Well, we grab the wrench handle and we apply a force perpendicular to the wrench handle. So I can push this way or I can pull this way. Now, why do I push or pull perpendicular to the wrench handle? Well, if I push along the wrench handle, that's not going to do anything to start this sticky nut turning. All I'll do is be pushing up against the nut. Likewise, if I pull along the wrench handle, all I'm going to do is pull the wrench off the nut. So for a force to have any effectiveness at trying to help me turn the sticky nut, I need to apply that force perpendicular to the wrench handle. All right, second element. It matters where I grab the wrench. All right, so we know from experience that I'm better off grabbing the wrench handle here and trying to push it or pull it perpendicular to the wrench handle than right here. This still helps me turn the nut if I push or pull perpendicular to the wrench handle here, but not as much as if I'm out here. All right, and then finally what matters, all else being equal, is how much force I apply. So for a given location along the wrench, the amount of force I apply perpendicular to the wrench handle impacts how effectively I can begin to turn this sticky nut. All right, so what is torque? Well, roughly speaking, torque is the effectiveness of a force in trying to help you turn a sticky nut. Now, what are the things that go into torque? Well, they're the things we talked about. First, what matters is the direction of the force you apply. Forces applied perpendicular to the wrench handle help you turn the nut. Forces applied along the wrench handle don't. So that's one element that's got to go into our mathematical description. Another element that goes into the description is how far you are along the wrench handle when you apply that force. Finally, the last element that goes into it is the amount of force you apply, all else being equal. So our mathematical description of torque needs to have those three elements, and we'll see that it does. The mathematical description of torque involves a cross product, so let's briefly review that here. Imagine I have vector A and vector B in the direction shown in the plane of the screen, as shown here. So now I want to take vector A cross vector B. Vector A cross vector B gives us another vector that's going to have a magnitude and a direction. The magnitude of vector A cross vector B, which I can write this way by putting vector A cross vector B between these absolute value signs, which by the way does not mean absolute value. In the context of a vector, these absolute value signs mean magnitude of that vector. So the magnitude of vector A cross vector B is equal to the magnitude of vector A multiplied by the magnitude of vector B multiplied by the sine of the angle between those two vectors when they're aligned tail to tail in a plane. So that's the magnitude portion. Again, A and B without the arrow symbols are magnitudes. This is a number. The direction of the vector formed by taking vector A cross vector B is perpendicular to both A and B. Another way to think about it is when you put A and B vectors together in the plane, tail to tail, they'll form a plane. The direction of vector A cross vector B is perpendicular to that plane. There's only two possible directions perpendicular to this plane. That's out toward you and in toward me. Which one do I take? Well, that's the job of the right-hand rule. So I take my right hand, take my fingers of my right hand and put them in the direction of the first vector in the cross product, curl them into the direction of the second vector in the cross product, and my thumb points in the direction of the appropriate perpendicular direction, which in this case is in toward me. Note, if I were to reverse the order of the cross product, that changes the direction. Vector A cross vector B is in toward me, but vector B cross vector A, I change the order. If I'm taking vector B cross vector A, I take my fingers and put them in the direction of vector B first, curl them in the direction of vector A, and then the resulting direction is out toward you. All right? All right, so that's our brief review of the cross product. Let's now apply the cross product to a mathematical description of torque. I'm going to write that up here, and then I'm going to unpack the description. There's a lot there, so let's unpack it. But first, I need to make a really important point. Torque is always calculated with respect to a particular reference point or a particular reference axis. In this case, we're going to take our reference point to be at the center of the nut. So now, using this configuration, we can calculate the torque produced by this particular force applied at this particular point about this particular reference point. In order to do that, I need to define this R vector. This R vector is a vector with units of length that points from the reference point to the point of application of the force. All right, so with that definition, I can say that the torque produced by this force applied at this particular point with respect to this reference axle is equal to this cross product, the cross product of R vector and F vector. That gives us the torque that this force produces with respect to this reference point. All right. Torque, being the cross product of two vectors, is itself a vector, so it has a magnitude and a direction. We'll talk about the direction in just a moment. Let's focus on the magnitude right now. All right, so to work out the magnitude of the torque vector, we can use our recipe for the magnitude of a cross product. The magnitude of the torque is the magnitude of the cross product, R cross F. To take the magnitude of this cross product, I need the magnitude of the first vector in the cross product multiplied by the magnitude of the second vector in the cross product multiplied by the sine of the angle between those two vectors. Now, the sine of the angle between the two vectors technically is supposed to be when the two vectors are aligned tail to tail. We see here I've got tip to tail, but I can correct that by just imagining sliding this R vector up to here, and then we'd see that the angle between the two vectors is this angle theta. Great. So let's take a closer look at this. When we do, we'll see that this magnitude formula for the torque contains all the elements we talked about earlier conceptually. So, all else being equal, the greater the magnitude of the force, the greater the magnitude of the torque. Secondly, all else being equal, the greater the magnitude of the R vector, the greater the magnitude of the torque. That corresponds to our earlier discussion about when we talked about grabbing the wrench further along the handle. Finally, the orientation of the force vector relative to the wrench handle, or now more mathematically precisely, relative to this R vector, matters because this angle matters. Remember, the sine of an angle can vary between 0 and 1, actually between -1 and 1, but we're only going to take angles that are up to 180 degrees, so between 0 and 1 for us. The sine of an angle is 0 when the angle is 0 degrees or 180 degrees. The sine of the angle is 1 when the angle is 90 degrees. So this angle will have its maximum sine value when the force is perpendicular to this R vector and hence perpendicular to the wrench handle. That corresponds to what we said earlier, that we get the best effect, the best turning effect, when we push or pull perpendicular to the orientation of the wrench handle, or more precisely now, perpendicular to the orientation of the R vector. Meanwhile, when this angle is 0 degrees or 180 degrees, we get no torque. 0 degrees corresponds to pulling that way directly along the wrench handle. 180 degrees would correspond to having a force this way, pushing directly along the wrench handle toward the nut. Neither of those should give any torque. That's consistent with this formula. I now want to talk about two alternative but equivalent representations of this magnitude expression for the torque. So to do that, let's look again at this figure. Imagine I drew a line along the direction of this force vector. I can extend it forever this way, and I can extend it forever this way, but it's got to be completely aligned with that force. Let's call that the line of action of the force vector. Now, imagine trying to draw another line that connects that line to the reference point, and imagine trying to draw the shortest possible line. Well, that shortest possible line that connects the line of action of the force vector to this reference point will be perpendicular to the line of action of the force vector. All right, I'm going to call that r perpendicular. And I'm going to show you that that r perpendicular is equal to the magnitude of this vector r times the sine of this angle. Here we go. So now this line and this line are intersecting each other. The two angles on the opposite sides of a vertex of intersecting lines are equal. So this angle right here is the same as this angle theta. So this too is theta, the same exact theta. All right, now since this is a perpendicular, then this is a right triangle. And so my right triangle has a hypotenuse equal to the magnitude of this r vector. This side is opposite this angle theta. So it's the opposite side, and it corresponds to sine of theta. The length of this side should be hypotenuse times the sine of theta, or magnitude of r sine of theta. So that's equal to this r perpendicular. So we can group this equation. I could group the r and the sine theta together as the r perpendicular, and I can conceptualize the magnitude equivalently to this as r perpendicular times the full magnitude of that force. Where r perpendicular is r sine theta, there's a conceptual name for it. It's called the lever arm. So if you take the line of action of the force and draw the shortest possible line from the reference point to the line of action of the force, that shortest possible line is called the lever arm, and I'm using the symbol r perpendicular to represent that. All right, there's yet another alternative representation. That's again equivalent to this. Instead, we'll imagine taking our full r vector. What instead we're going to do now is look at the force vector. We can break the force vector into components. I could break it into a component that's entirely perpendicular to the r vector and one that goes entirely along the r vector. And now this component could turn out to be parallel to the r vector or anti-parallel to the r vector, for example, if this force vector actually were this way. The key thing is it's right along the r vector. So we know that a force component along the r vector, whether it's this way or this way, will produce no torque. The entirety of the torque produced by this force will be produced by the component of that force that is perpendicular to the r vector. So I can call that component of the force that's perpendicular to the r vector, I can call it F perpendicular. So I can conceptualize the torque as this full magnitude of the full r vector multiplied by this F perpendicular, and that would give me the magnitude of the torque vector. Again, now F perpendicular, I should point out, is just F times sine of theta. We can see that. Right here I have a right triangle. So if this is my F vector and then these are the components, this one's parallel to the r vector, this one's perpendicular to the r vector, this makes a right triangle. I could actually put this over here. This F perpendicular is really the side of this right triangle that's opposite to the angle theta. Opposite goes with sine. So the magnitude or the amount of this will be the magnitude of this times the sine of theta, or F sine theta. So all I'm doing is taking the F sine theta and replacing it with the symbol F perpendicular because of the same thing. So this and this and this all give us the same thing. They're all mathematically equivalent. But sometimes there can be shortcuts thinking about this. Sometimes it's easy to identify the lever arm by looking at the line of action of the force. Other times it's easier to take the force and quickly break it into components and identify the component of the force that's perpendicular to the r vector, and sometimes it's easier just to grind out the full-blown magnitude formula. Let's now consider the direction of the torque. The direction of the torque vector is necessarily in the direction of r cross f. And remember, the direction of a cross product of two vectors is perpendicular to both those vectors in the direction given by the right-hand rule. So, to get the direction of r cross f, I take my right hand, I put my fingers of my right hand in the direction of the r vector, curl them into the direction of the f vector, and my thumb points in the direction of the torque. That's toward me. Well, what does that give you? Well, the direction of the torque vector is the direction of the angular acceleration that would be produced if there were no other torques. So what that means is the angular acceleration of the torque that this force produces is toward me. Well, in a planar sense, what that means is the thing will start to rotate this way and go faster and faster. All right, so going from no angular velocity to an angular velocity this way corresponds to a planar sort of description of angular acceleration that's this way. But an angular acceleration, described by sort of a planar direction this way is really an angular acceleration that's out toward me. Sticking your fingers of your right hand in the direction sort of the planar curving direction, your thumb points in the direction of the angular acceleration vector. Let's find the direction of the torque in another example. I'm going to take my reference point to be at the center of this nut. Imagine there's a force, F, being applied right here in this direction, and I want to find the direction of the torque that this force produces about this reference point at the center of the nut. Well, my r vector points from the center of the nut to the point of application of the force. To get the torque, I would calculate this cross product, and to get the direction of the torque, I'd use the right-hand rule for the direction of the cross product. I'd take my fingers of my right hand, stick my fingers of my right hand in the direction of R, curl them into the direction of F, and my thumb points out toward U. So the direction of the torque that this force produces about this reference point is out toward U. What that means is, in the absence of any other torques, this force would cause a torque that produces an angular acceleration with an angular acceleration vector out toward you. An angular acceleration vector out toward you corresponds to a sort of in the plane description of something going faster and faster and faster this way. All right, so hopefully that helps with the direction of the torque. All right. That's all for now. Thanks for watching, and I'll see you next time.